So we're now going to discuss the Burali-Forti paradox. This was introduced by the Italian mathematician Burali-Forti. It was published in 1897 in a Sicilian journal of mathematics, actually. And it was the first of the so-called paradoxes of said theory to be published. So it came about in the following way. So what we've seen is that if we think of ON as the class of all ordinals, class of all transitive classes well ordered by epsilon, then Burali-Forti, he observed, just as we've done here, that ON is a class itself well ordered by epsilon. Class well ordered by epsilon. But then this is precisely a class just like that. So in which case, ON should be a member of itself. And you can see the relations perhaps to some of these other paradoxes here. But then epsilon isn't well ordering ON. Right? It's not a strict total order because we've got ON is a member of ON, right? And a strict total order is not going to be reflexive like this. So it's a contradiction. So reception of this was somewhat messy, right? Burali-Forti thought that he'd shown that the ordinals were not well ordered. Bertrand Russell, a year or so later, thought, oh, well, what Burali-Forti had proved was actually that the ordinals were just linearly ordered. Right? They weren't in a well order. So there were difficulties about this, right? And it wasn't until Russell came up with this idea about thinking about proper classes and sets that we saw that this kind of reasoning here is not legitimate. I mean, here you can see I said the class of all transitive classes well ordered by epsilon. Right? So actually what Burali-Forti shows is, in its modern form, right, is that ON is itself is not a proper class, right? Sorry, is not a set. So we can't write that ON is a member of ON here. So this is the next lemma, 325 there in the notes. So let's go through that argument, which I've just done sort of verbally, but in this modern setting, but in our setting. So this is lemma 325. Right, so this is the Burali-Forti lemma. So what was a paradox, in the end, becomes a theorem. Right? ON is a proper class. So we suppose that it's a set, we get a contradiction. Suppose ON were a set. Okay, let's call it Z. Say, here. And we've seen that Z epsilon here On is a transitive class. So Z is transitive. And we've just seen that On is well ordered by epsilon. So these two facts together mean that Z is an ordinal. So that is, Z is a member of Z. Right? Because Z is On. But this contradicts the fact that this is a strict ordering. And we have that Z is less than Z, right? Whereas this is not a reflexive ordering. It's a strict total order. So it's a contradiction. And the supposition is false. Here. So On is then a proper class here. But it took a couple of years to get this thinking straight, get all of this worked out correctly. Right. What we're going to do now is look at some ways of thinking about ordinals, perhaps more sort of informally, viewed perhaps as pictures. So top of page 31 here, we're going to define in general how to add and multiply orderings. Not necessarily well orderings. So definition 326. So we've got two orderings, right? I'm going to think of them as strict total orderings, not necessarily well orderings. So we've got AR and BS. These strict total orderings. They're always going to be strict, so I may drop this word here. So we define the sum ordering, and we're going to call it CT. And basically the idea is, just as we did at the very beginning, we thought of the odds as coming after the evens in an ordering of the natural numbers. I'll just think of AR coming before BS. So all C does is just incorporate that. So the field of C will be the field of A together with the field of B, and we'll put the A things coming before the B things, and that's what T will do. If I've got two A things, T respects R, and if I've got two B things, T respects S. So I'm just putting the two together. So we'll assume that A intersect B is empty, that they're disjoint. So when I take their union, I'm not going to confuse which things are under the R ordering and which things are under the S ordering. So the idea is we've got a copy of A here first. This is AR. And now comes BS. Not necessarily well orderings here. So C will just be A union B. Right? And T just says what it has to say for this picture to hold. Right? So we're going to put UTV if and only if U and V are in A and U comes before V, or they're both in B and U comes S before V over here in the B ordering, or U is in V and V is in B. U is in A and V is in B. So that puts the A things before the B things there. So that's how I define T here. But the intention is this picture. Right? Now the point is, if AR and BS are well orders, so is CT. And that's the next exercise. If AR and BS are well orders, so is CT. So we know that they're strict total orders. It's fairly obvious to see that CT is a strict total order from the picture, right? So then argue that AR and BS being well orders implies the same for CT. So this now gives us a way of defining a prototype for addition on ordinals. Suppose I've got alpha epsilon and beta epsilon, and the Greek letters are now restricted to ordinals. Then we'll define alpha plus beta, and I'm going to use a little prime here because this is not going to be my official definition of addition. That will come later, but it will coincide with this informal picture that we're building up here. But I'll call it plus prime for the moment, right here. So this is going to be the ordering, and the idea is it's a picture of alpha followed by a picture of beta. So this is what alpha plus beta will be. This will be the ordinal that corresponds to the order type of this picture that's here. So it's going to be this order, alpha, plus this order. I should have said here CT is we're going to write this as AR with a plus BS here. And I think not. No, I'm going to use this. I'm going to call this, let's just call it for today alpha plus prime, right? Now there's a little wrinkle here because I did specify that A and B have to be disjoint, right? And that's not quite going to be the case here. For example, if alpha is less than beta, actually alpha is a member of beta and a subset of beta. So it's far from disjoint. So we just apply a little disjointing trick that one uses. Instead of thinking of the field of the sum ordering to be this ordinal, these ordinals, and these ordinals. We'll pair these ordinals off with 0 and these ordinals off with 1. And then that keeps the two things separate. So here, actually, I'm going to write alpha cross empty with its, I'm going to have less than here. And then I'm going to add on to this beta times Cartesian product with 1 with less than. So over here, I've got all the ordinals in alpha in the first part of an ordered pair, paired off with 0. Here I've got all the ordinals in beta, paired off with 1. So now this set is disjoint from this set. Which is what I wanted to define the sum ordering here. Right? I don't want them overlapping or getting mixed up. So we're going to look at the sum ordering then of these two. So in short, we shall write alpha plus beta here to be the order type here of this set. Under the ordering, the sum ordering, which we are calling T, or in this case, plus. Let's keep with T. And so just to write it out again, right? If I could take any gamma cross 0, this becomes before any delta cross 1 here. And I've got any gamma 0. Right. What do I want to say? I'm going to put UV. If U is of the form gamma 0 and V is of the form some delta 1, or U is of the form gamma 0, V is of the form delta 0, and U is less than delta, or they're the same thing, but we put 1s in here. So this way, we can define a kind of addition or sum ordering then here on these. So, but really it's just easy enough to think of pictures. And what we'll see next time is various properties of this addition idea. So examples. What is omega plus 2? It's a copy of this followed by a copy of this. So here's a copy of omega. And after it comes a copy of 2, 0 and 1 here. What is 2 plus omega? It's a copy of 2 followed by a copy of omega. Here's a copy of 2. And now comes the copy of omega. Here's the copy of omega in the first one. And here's a copy of 2. So the first thing to notice is these are completely different. This picture is indistinguishable from omega, whereas this picture is quite different. In here, this ordering, there's an element which is non-zero and has no unique predecessor, no immediate predecessor. Sorry. That's not the case here. Every point does have an immediate predecessor if it's non-zero. So what we're going to have is that our ordinal addition is not going to be commutative. Ordinal addition is not commutative. So this is the first indication that things are going to be a bit different from the finite. We're going to have that 2 plus omega is not the same thing as omega plus 2. So next time, we're going to see how to do multiplication using these kinds of pictures.